All right. Hello, everyone. Thanks for tuning in. This is Mr. Puig. I'm going to be talking a little bit about something we've already seen before, but that I just want to briefly kind of review. I don't think I actually reviewed it in the right context. And what I mean by that is last semester, we talked about the wave speed equation. And if you remember, this is a lambda sign. I know it looks awful, but that is supposed to be the Greek symbol lambda. And if you multiply that times the frequency of a wave, then you will get the wave speed or velocity. That's why it's a v. Now, lambda represents, if you remember, wavelength. Whoops. Wave. Let's put it down here. Length. Okay, and then F was for frequency. And V, again, was the velocity of the wave. Or we also call that well, they're not identical, but the velocity or speed of the wave. And this is, we learned about this last semester. Basically, you take the wavelength, and this could be, in meters or centimeters, whatever the length is. The frequency is something else. It's called a hertz. That's the unit of frequency we generally use. So if you keep this in meters, you use hertz. And let's say we put a 1 here and a 2 here. 1 times 2, that means we're going to get a wave speed of 2 meters per second. Okay? And I just want to clarify something too. I'm going to erase this, but so hopefully you have it written down. If you don't, just go ahead and pause it. So what this basically means, and you got to understand this, is that frequency and velocity of a wave get kind of confusing. So frequency is very similar to velocity, but different. So if we just draw, a normal wave that we see, okay, the frequency, and I'll just draw this line here, it goes through the middle usually. The frequency, if this is a given point in time, okay, we want to know how many of these waves. So we designate one wave from crest to crest or from trough to trough. Okay, so that's like our T, our trough, our crest. It's the top, like a cresting wave. Okay, this is one wave. How many of these waves, so this is one wave right here, how many of these pass a certain point, okay, in a given time? That's our frequency. Okay, wave speed is going to be actually how fast the wave itself is traveling this way, okay, or whatever way it's traveling. So in this case, we're traveling to the right. So you could think of it as like a point on the wave. How fast is that point traveling? Okay, so that is the speed. Now, that's something we learned last semester. What I don't think I differentiated, and so we need to do it right now, is that last semester we were learning about mechanical waves. Okay, so mechanical waves are waves that propagate, as you can see up here on the left, are waves that propagate through a medium, or they require a medium to travel. And I'll put that in red so you can see a little bit better. So mechanical waves require a medium. All that word medium means is matter or stuff. Okay, and there's stuff or matter all around us. Okay, so we talked about earthquakes, right? Earthquakes, sound waves. So I'll write it down. Earthquakes, sound waves. Oh, Wall Street Journal. And then earthquakes, sound waves, and we even talked about, water waves. All of these are basically showing energy moving through a medium or matter. Okay, a wave is really just how energy travels. And mechanical waves are, earthquakes, sound waves, water waves. All of these require matter. So hopefully we got that down. Now, what we're learning about this semester, and what we're starting out with, is electromagnetic waves. So by definition, electromagnetic waves How do we know they're electromagnetic? Because they do not require matter. Okay, so, we see this right here on the right, this definition, and I'll put it in red. Give me one sec. Okay. They do not require a medium. They definitely can travel through mediums, okay, but they don't necessarily have to. So these are waves that don't require a medium to travel through, but they can travel through medium. And the best example is obviously electromagnetic waves or electromagnetic radiation, which we actually the most common electromagnetic radiation we deal with is light, right? Or what we refer to as light or visible light. Okay, but really light is a spectrum, as we learned last week. And so light waves do not require a medium. And this is really important for what we're learning about right now, because where do we get all of our energy on the surface of the Earth? In other words, we're learning about the external engine of the Earth. Where does the external engine of the Earth get its energy, right? And so we know engines require energy, and we'll talk more about what the engine even does. And we just want to start out with what causes these changes on the surface of Earth. And you guessed it, it's the sun. So the sun, but how does the energy from the sun get to our planet that's really far away? Well, far away for our standards. And so we'll just say this is planet Earth. And I'm going to represent the vacuum of space. So space, if you didn't know, if you're truly in outer space, then space is devoid of matter. Okay? In the sense that we're used to. There's no atmosphere or anything like that. So how does the light ray, how does this energy get from the sun to the Earth? And the answer is obviously through electromagnetic waves, because we know mechanical waves can't travel. So if we have let's say we had sound waves, okay, sound waves in blue. These would not travel, okay? And we know this because sound doesn't propagate through space. But we know that light waves do, so those are electromagnetic radiation. Okay, and so they reach the Earth. And we're going to dive deeper into this later this week and why this is important. But obviously, just you could kind of guess, it's because all energy that even the energy that is required for me to speak as I'm speaking right now, came from the sun, originated from the sun. Because the sun, send electromagnetic waves to the Earth. That energy is stored in plants. I ate the plants, and now I am breaking down the plants and getting that energy back out. So energy is always being transferred around and all that good stuff. But anyway, so electromagnetic waves don't require a medium. They can travel through space. And so I just want to add this. We're going to be doing a couple problems, really simple problems, like we did last semester, so don't be too stressed out by the math. Remember, these problems can be... I could make them really difficult, but for this class, as you can tell, the variables make it kind of scary, all these weird letters, and I know a lot of people are like, when there's letters in math, that's when I check out, right? But I give you the numbers, and it's really easy. So basically, let's just put this wave speed equation back up really quick. All we're going to be substituting is because, and you know what, let's, on the Edpuzzle, I'll make sure this is a question before we go any further, but if hopefully anybody remembers, if you remember from the Edpuzzles last week, what do we know that electromagnetic waves can do in a vacuum? Or how fast do they travel? And hopefully remember, and I made that a question in the Edpuzzle, but hopefully remember the answer is the speed of light. And that's actually represented by another variable, which we call c. And it's really, really close. It's actually technically a little bit less than this, but it's 3 times 10 to the 8th meters per second. So you do need to memorize this. And when we do problems, I'm going to have to give you calculators that make this easy to solve, or we'll just have to solve them on the iPads. Obviously, you won't really be required to do this by hand, but basically we put that right there because that's the speed of these waves in the empty vacuum of space. And then obviously they slow down and all that stuff when they hit matter. So anyway, that's that. We will be doing some problems where we solve this, so I could give you the wave, and we'll be practicing. I could give you, let's say if I gave you the wavelength of a wave, of an electromagnetic wave of 3 meters, okay, let's say 3 meters, and I wanted you to find the frequency. Simple algebra says we would divide 3 by c, 3 times 10 to the 8th, and that would give us our frequency. And that's how many times this wave is passing in a given second. And obviously we know it would be, the frequency would be extremely, small number. The frequency would be very small because 3 divided by this massive number. By the way, what is this number? Can anybody figure it out? The times 10 to the 8th means that's how many zeros we add after the 3. So that is 1, 2, 3, 4, 5, 6, 7, 8. So that is 300 million meters per second. And that number would be bigger if you calculate it, which we're more used to seeing in miles per hour. So 300 million meters per second. So if you've ever seen a meter stick, this is still even hard to, obviously it's just too hard to comprehend, but if you've ever seen a meter stick, it has to travel 300 million meter sticks if you line them all up in 1 second. That's how fast light travels. And just to give you some more background on that, there's how big space is, just as a side note. There's, you've probably heard of things, the nearest sun being light years away. So that means how far light could travel in 1 year, and light's traveling 300 million meters per second. That means those things are really almost, incomprehensible. But anyway, so that's just kind of the note here. We're going to be solving some problems where we substitute c in for the velocity. And I want you to know the difference between mechanical waves and electromagnetic waves, and what a medium is. A medium is basically just matter. And we'll move from there, and we'll start to understand how this relates to the external engine of the Earth. All right, I'll see you guys later.